Let's do that.
Okay, so welcome to the Ground Source Heat Pump Association Training Academy and the latest in our webinar series. It's been a while since we've hosted one of these sessions. I think we've all been very busy, so that's the main reason why. Stephen Bilby, our General Manager, is with us today. He'll be looking after questions. So please post your questions in the chat. It really helps me to make the session more interactive and push the session in the direction to which you're interested if you ask those questions as we go through. Stephen will interrupt me. There will be time at the end for more questions and any wrap-up questions that come out. But please do interrupt me as we go through by putting some questions in the chat, and Stephen will ask them of me.
We've also got the question and answer button as well, Chris. So it's chat and question Q&A buttons, so they come to both. Okay, super. That's fantastic. So yeah, please use those facilities to interact with us today. So welcome. As I say, my name is Chris Davidson from Genius Energy Lab. Today we're going to do not a PowerPoint, we're going to do a whiteboard session. So I'll be scrolling around the screen and scribbling on the screen. So my name's Chris Davidson from Genius Energy Lab. I've sat on the council of the Ground Source Heat Pump Association for many years now, and I chair the Policy Development Committee for the Ground Source Heat Pump Association. So involved in the lobbying side of things, but my day job in Genius Energy Lab is designing ground source systems of all sizes, really. So we're involved in the design of what we're going to talk about today, which is ambient heat networks. So what I'm going to do first is I'm going to define what an ambient heat network is. Now that definition is far from fixed. It's far from it is controversial. And so I'll just bear that in mind as we go through, and I'll talk a little bit more about why that should be the case in a second. What I'm then going to do is talk about residential schemes, so multiple residential dwellings fed by ground source heat pumps in general, specifically focusing on low temperature heat networks. And I'm then going to talk a little bit more about the hydraulics of that and how the considerations that need to be put in place to design those hydraulics. What this isn't is a design course. So I'm not teaching you to design ambient heat networks. It takes people, even within my company, several months to get up to speed with basic design. So this is an hour overview of what the technology is and how it works. I'm then going to go on and talk about how this applies to mixed networks, so not just multiple residential, but mixes of other types of buildings as well. Okay, so assuming there's no questions on the chat, Stephen, I will start. Yourself, you're all clear there, Chris.
You're all clear. Great stuff. Thanks, Stephen. Okay, so let's give you a bit of context for heat networks. There's been a lot of discussion over the last few years about the generations of heat networks. I've tried to summarize this in a number of slides. This isn't the chapter and verse on the subject. There are some vagaries around it, but I've just tried to give you a definition of it. So the first generation heat networks were installed 100 and more years ago. They were typically running above 200 degrees. They did tend to include some kind of heat storage in those networks and were principally fueled with coal waste. And so those heat networks were relatively low efficiency, COP less than 5. So for every kilowatt of energy, native energy going into them, they were delivering less than half of that into the dwellings. The pipes were relatively small, which allowed, and that was allowed because there was a really big temperature difference in those networks. And the pipework wasn't that well insulated. So the overall architecture was not very efficient. So moving forward to the main of the part of last century, we're talking about now second generation heat networks. Temperature still above 100 degrees C, so still steam in those pipes. Pipes, again, relatively small with large temperature differences in those networks. COP probably creeping above 0.5, half 50% efficiency, and the insulation in those pipework were getting better. So improvements, but still quite a long way to go. We then get into the third generation heat networks, which were installed up to really a couple of years ago. So temperatures now less than 100 degrees C. temperature, COPs around 1, depending on the source of energy. But we started to get much more diverse sources of energy included in these networks. So from large-scale solar, biomass, industrial surplus heat, combined heat and power waste, and so on. So more efficient networks as a result, as the temperatures dropped. And also the insulation values in the networks did increase. Fast forward now to what's happening today, and we are really seeing the mass rollout of 4th generation heat networks. Now I'm going to talk later about 4th generation heat networks in the context of ground source. So yeah, ground source is a source for a lower temperature 4th generation heat network, and in our company we design these things regularly. So highly insulated pipes, heat pumps starting to become the primary source for these networks as we get off gas. And the efficiency therefore improves depending on the source. It could be a blend of sources. You're looking at 2 and above, really, if you are, you look at 2 and above for a heat pump network, at least 2 really. So what are we talking about in the main today, though, is 5th generation heat networks. Now, as I say, this definition of 5th generation heat network is far from decided. It's a bit controversial. Lots of people in the more conventional heat network space really argue against heat networks running below 20 degrees C as being defined as a 5th generation heat network. But for the purposes of today, we're going to define those 5th generation heat networks as running between 0 and 25 degrees C. They've got much higher coefficients of performance in those networks. They'll be either running for central air and ground source heat pumps or a ground loop. There'll be uninsulated pipe moving that water around to the heat pumps, which tend then to be distributed at a building or even distributed around a building. So a very different heat network architecture, by which you've got lower temperatures, potentially uninsulated pipes, certainly below ground, distributing that energy around at effectively ambient temperatures. Heat losses, therefore, become not a problem, but a benefit. So when we start to run those heat networks down below the temperature of the ground, they suck heat from the ground. So they've got negative losses in that regard. Now, I'm not explaining today how heat pumps work, how ground ground loops work and how they're designed. We've got plenty of webinars on that in the series, so please do check the wonderful new training section in the Ground Source Heat Pump Association website, where you can find out all sorts of things about ground source, the stuff in the ground that I'm just going to gloss over really today. So please do look that up. While you're there, it's also worth checking out the Ground Source Heat Pump Association Training Academy. That will be launching very, very soon. It's in the final stages of development. All the videos are created now for Stream 1, which is intended for consulting engineers, perhaps energy managers, those types of people who want to get a really strong grounding in ground source so that they can specify it properly, they can communicate effectively with the specialists in the business. So I really would encourage you to have a look at that. One final thing before I move off this, the efficiency of the things. The efficiencies of these heat networks are dramatically higher than previous heat networks. You'll see once you start to get into adding renewable energy to these networks, and particularly when you start to look at heat pumps, you will have a range of COPs. One of the things I'll really strongly emphasize to you is there is a massive difference between the COP, the rating point COP, coefficient of performance, of a product and the seasonal COP of a network. The seasonal COP of a network depends on the temperature of the source, which, be it air source or ground source, will vary across the year. So it's really important not to try and compare the boiler plate, if you like, COP for a heat pump product and call that the whole story as far as the seasonal COPs are concerned. Okay, so I'll just make that point now. Stephen, have we got anything? Be a good time to take any questions if we have any.
At the moment, you're okay, Chris. No question.
Okay, stunned silence, is it?
Must be.
What's he talking about? Okay, right. So
two people here, so it must be, must be someone who wants to ask you something.
The reason I ask, part of the reason I ask you, have I got any questions, because I need to take a drink and keep my throat lubricated. Okay, so let's look at the applications of these heat networks. So this is a 4th generation heat network fed by ground source. So what you'll see right away, we've obviously got a ground loop here, which is, in this case, it's a heating only network that is sucking heat from the ground. And we can talk about in another session about how we design those loops. We have talked about it before, how those things need to be designed to be sustainable in the long term. But for today, just take it, there is something in the ground. I'm going to draw those ground loops today as borehole systems, but again, in previous sessions, there is plenty of coverage of other solutions, mine workings, open loop systems, horizontal systems, and so on. So I'm going to concentrate now on what goes on inside the building. So what we have here is some central plant, drawn some heat pumps there, and they are delivering heat up a single high temperature riser, and the heat is being delivered into those dwellings via heat interface units. Okay. Now these heat interface units will be delivering domestic hot water, and that might be at, say, 65 degrees C. Okay. They'll also be delivering space heating, and that might be at 35 degrees C. Sometimes, well, often higher, but let's take an extreme example at 35 degrees C, perhaps into domestic hot water, into underfloor heating, for example. Now, because we've got only one riser here, that riser has to operate at the higher temperature, or the highest temperature that heat interface is then going to be delivering. So that heat network needs to run up at 65 degrees C. And the important thing about efficiency on heat pumps, it doesn't matter what you do, how clever your product is, the efficiency of that system is proportional to the temperature difference, inversely proportional to the temperature difference between the source and the load. So for a given source temperature, we are running all of our space heating and domestic hot water up at 65 degrees in this example. Therefore, we are compromising the efficiency of that heating. We're not maximizing the efficiency of that heating because we've only got one district heat network. So there is always inherently a compromise in this, unless you're going to go to the extreme of having perhaps two networks, one running at low temperature space heating, the other running at a higher temperature for domestic hot water. Final point I make on these is the really important consideration is that this heat interface unit represents a commercial opportunity in that you are selling the kilowatt hours of heat being delivered into that project. So commercially, this is a very specific proposition with central plant and ground loops owned and operated by an ESCO, for example, and that heat billed by the kilowatt hour into the property. So it's a very specific technical and commercial solution.
Chris, we do have a question.
Wonderful.
So what would your opinion, what would be your opinion on the biggest challenges when designing ground source heating and cooling networks when compared to individual ground source heating and cooling systems?
That is a really good question, and I'm actually going to cover that in a minute or two's time. So can I just put a pin in that question, and I'll answer the answer for you with a case study actually of how we design these networks up.
Okay, I've also got a comment as well that's come in. It is not really accurate to compare different COP from first generation and COP from fifth generation. In one case, primary energy is coal, while in fifth generation is electricity, which is actually produced out of a mix.
Absolutely agree, and I fully acknowledge the compromise there. I was just trying to give you a flavour for it. So yeah, if you want to get into the detail of the sources, I would need 1,000 drawings to talk about the efficiency of the various different mixes. So yeah, hands up there. That is a simplified explanation of a very complex topic. So yeah, absolutely agree with you.
That's everything, Chris. You've got the moment.
Thanks very much indeed. Yeah, no, it's super. I meant to make that point actually in what I was saying. So that is a fourth generation ground source district heat network. I've drawn it as a tower block. Doesn't matter. Could be low rise. Could be anything. If we now compare that with what I've defined as a fifth generation solution, and again, there is controversy around that definition. What we've got now is a ground loop in the ground, just as we had before, but we are now delivering that ground loop water to individual dwellings, and in each dwelling, we've got a heat pump now. A couple of things to point out. First of all, we've got no central plant here, okay? There is no central heat pumping going on here, and there's actually no central pumping required. Some prefer to have central pumps in their solutions. I certainly design those out, and what we actually do is spend an awful lot of time on the hydraulics of these systems to make sure that the tiny little circulation pump that's inside this heat pump can deliver enough water to that heat pump if there's one heat pump running, or as I've drawn it here, if all 12 heat pumps are running. And that could be 200 heat pumps as well. So the hydraulics of these systems are very, very complex and take quite a lot of designing. So just bear that in mind. So what does that give us? A couple of things. First of all, this heat network's now running at ambient temperatures, running between 0 and 25 degrees C. It would be down at 0 if this was just a pure ground source. It would touch 0 at the end of 20 years as the typical design parameters for ground source systems. If we've got any energy recovery going on, however, then it could be higher than that. And we tend to limit it to about 25 degrees because if you go above 25 degrees, heat pumps, when they're heating, tend to fall over on high pressure lockouts. Depends on the heat pump product involved, but it's a general principle again. Okay, so these heat networks are running between 0 and 25 degrees C. So whilst we do need to insulate them above ground against condensation, we don't have to deal with the higher levels of insulation that water up at 65 degrees would. So that's a change in the philosophy there. Second thing is, we can actually get this heat pump to do domestic hot water when it is required at the temperature at which it is required. So say 65 degrees, to keep it consistent with my previous example. It can then turn off that domestic hot water and go down to the space heating temperature at, say, 35 degrees, again, to keep it consistent. So we're only actually going up to that higher temperature, which is a lower efficiency regime for a heat pump, when we have to. So that is a very important point to make, that we're only doing one or the other. Okay, we are taking advantage of that low temperature space heating, taking full advantage of that by only doing that or the domestic hot water, but never both together. So it's a very, very different engineering proposition. The other point to make on this, to compare it with the other, is the run costs of that dwelling are entirely related to the electrical energy that's being consumed by that heat pump. So the tenant in that dwelling, or the owner of that dwelling, can purchase their electricity from whoever they want, and they have flexibility with their fuel purchase agreement. So again, a very different ownership proposition. So if you look at the two, technically and commercially, they are very different propositions. Okay. The commercial agreements around the sale of the heat or the purchase of the electricity are very, very different. So if you contrast a couple of examples, let's say this one here is a new build housing development where an energy service company can be built into it, and the sale of that heat can be built into the overall agreement for the development. Then that might be the best solution. If you perhaps look at a more social landlord type arrangement, where the social landlord perhaps doesn't want to get involved in billing and metering of that heat, then this solution will tend to come into its own. So both technically and commercially, these two solutions are very, very different. Okay. Any thoughts in the chat?
Yes, Chris, there's one here. In your experience, what is a common practice when operating ground source heating and cooling networks? Is a network operated by a private company and then selling the H&C loads, or is it consumer owned and shared, or even public owned?
Most of the designs that we've done over the last few years will be, well, let's say a mix is probably the best answer to that. There are increasingly community-owned heat networks. There are increasingly utility-owned heat networks. We're designing a number of town-wide heat networks at the moment, which will be third-party ownership of that ground loop as an infrastructure asset, potentially third-party ownership of the heat pump as well, and then heat being delivered as a service. So they're coming more to their own, more to the fore at the moment. But traditionally, it's more been a building has purchased that ground source system, and we'll be looking at the payback on the lower cost of ownership as the reason for doing it, and indeed carbon reduction as well. So a mix of all sorts, but the utility ownership, the third-party ownership, the ground loop as an infrastructure asset is becoming more and more into the fore now. So yeah, sorry, that wasn't a very concise answer, but it hopefully gives you a flavour for it.
Mix, got it sorted to me. One more, Chris, for you as well. What is the difference in CapEx between the two solutions?
That's a great question, Duncan. Thank you for reminding me. I bet I came in from Duncan, did it? You always have to remind me.
Correct.
Yeah, okay. So Duncan's my colleague, and I forget this all the time. So we've done a lot of studies comparing and contrasting the commercials of these systems, and it's remarkable how close the capex is between the whole system. So if you take everything there, including the heat pumps, and you take everything there, including the heat interface units on the heat network, the capex is remarkably similar. Whilst the cost of the heat pumps generally here will be lower, cost per kilowatt of big heat pumps is going to be lower than smaller heat pumps, the overall cost of the networks are remarkably similar, to the extent where we did a study a few months ago on a megawatt scale heat network, and the capex was around £4 million, and it was about £4,000 difference between the two. So it's that close. This one was about £400 more expensive to install, £4,000 more expensive to install on a £1 million system. So very, very close in terms of install costs if you take it in the round. So great question.
Okay, one more, Chris, coming in fast now. In new build developments, is it better to have a single ambient loop serving many properties, or to break it up into multiple smaller ambient loops?
That is a brilliant question, and it brings me beautifully onto my next slide. So thank you very much.
I've just got one more to set you back
Go on then.
CapEx thing. So if CapEx are similar, is there an interesting difference on energy efficiency?
Yes, generally speaking, this one will be more efficient overall. Right. Because you're not compromising your space heating efficiency here by running that up at the domestic hot water temperature. You don't have that compromise in this network. As a generalization, it is a case-by-case basis, particularly when you start to consider energy recovery being added to these systems. But that's as a general principle, this distributed solution will come out technically the better solution.
And in regard to soil saturation, that's the second part that's just come through now.
Okay, I don't really want to go into ground loop design too much today, but no matter what you're doing with a ground loop, you must ensure that it's sustainable in the long term. So what we mean by sustainable in the long term, if we look at a heating only system, we want the evolution of temperature in that ground loop to, it will do something like this between winter and summer. What we don't want to do is see that just keeping going colder and colder and colder. We want this design to be tending to a limit. And that limit needs to be well within the capabilities of the heat pump. So that's the kind of parameters we put on ground loop design. Heating and cooling systems will be slightly different. They'll do this winter and summer. And again, you don't want that just going up and not going down. You want these tending to a limit. And you want that limit to be within the sweet spot for your heat pump performance. Okay, so very quick overview. If it is getting colder and colder, it's not a big enough ground loop, not a well-designed ground loop, simple as that. And we've got more sessions on that in the webinar series. And if you want to get into real good detail on it, stream 1, the training that I mentioned for consultant engineers, we get into it in quite a bit of detail there.
Okay, cool. Does the HIU primary rhetoric pump replace central pumping and therefore interact with all HIU rhetoric pumps?
I'm not sure I understand the question. Perhaps you could clarify in the chat.
Pump, I've misread it. Does a HIU primary research pump replace central pumping and therefore interact with all HIU research pumps?
It can do, is the answer to that, yeah. There are different architectures. In fairness, I'm not an expert in high temperature heat networks. My bit is in the ground and up to the heat pump. So yeah, perhaps it might be a good idea for a future webinar, Stephen, to get a heat interface unit manufacturer to talk about fourth generation heat networks and how heat pumps and heat interface units work together. That might be a really interesting topic actually for a future webinar. So yeah, I'll crack into a couple of slides and perhaps we can take in a couple of questions. Is that okay?
That's fine, Chris.
All right, so you asked about how we design these heat networks. Do we break them up? Do we stick them all together? How does it work? And the answer is you've got options, okay? So let me show you an example here. This is a heat network. It could be 6 commercial buildings. It could be 6 dwellings. It could be 600 dwellings. Doesn't really matter. It's just an illustration. If we've got a good number of buildings connected together, then we can take a diversity factor on the heating profiles for that buildings. So you can assume that not all these heat pumps are going to be running at the same time. Okay, so one's off and the other 5 are on in this instance. Now that might allow you to get away with a bit less borehole, fewer or less deep boreholes. So it's going to give you a better borehole installation cost. Diversity, if you want an illustration, is when you're designing an electrical system in a house, you don't assume that there's a 3-bar electric fire plugged into every socket. That would be over designing the wiring, exactly the same as that. Okay. The downside of connecting everything together is that this pipework, this header pipework, starts to get big because you're transporting enough water now to feed all of those heat pumps around the network. Now, you can take some diversity in assuming again that all the heat pumps are running. The pipework can start to get quite big. So what you've got as an alternative at the other extreme is to break these heat networks up. So this is the other extreme where we've got 2 dwellings perhaps connected to a single ground loop. Now that might mean you've got a bit more ground loop to go in, but it keeps these header pipe sizing right down. And in actual fact, in this instance, the header pipe sizes could be smaller than the borehole pipe sizes and still give you an acceptable pressure drop in the system. There's an excellent session hosted by Robin Curtis on pressure drop, which we did a couple of years ago now. So it's worthwhile having a look at that. So our design is a balance between connecting all together and getting a maximum diversity or distributing it. The other reason you might want to connect it all together is, let's say, for example, we've got a solar farm connected to this ground loop. So you'd want that heat from that solar thermal to be transporting around your whole network. That might be a solar farm, it could be any other waste heat from sewage, whatever, doesn't really matter. And that would drive you towards that connected heat network. So what you tend to do in the real world, and this is a real case study which is just completing its installation, credit to Kenza Contracting for this. This is a new build housing estate in Wales called Park Erin. And if I zoom in here, you can see that we've got 5 boreholes here in the blue circles, which are connected to 10 dwellings, I think it is, in that little array. So that's one array. So we've kept our header sizing down, but we're up to the point where we can be considering some diversity with those 10 properties, because everybody's not going to be occupying them in the same way. Okay, so hydraulically, that's pretty straightforward. If I look up here, there is a little bit of subtlety to this, because let's look at array 29 here, 2 boreholes here, and let's look at this array here, 28. That borehole there and that borehole there, they are close enough to that other borehole. Whilst they're not hydraulically connected, they will be in thermal contact with each other. So when we are designing these systems, we can't just design each individual array on its own and stick them together and expect them to work, because they will be in thermal contact with each other, even though they're hydraulically separate. So when we design a heat network like this, we've got to ensure that we are modeling the heat network as a whole, as well as those individual arrays. And in this instance, you'll have various depths actually across. So those 2 boreholes there, feeding those dwellings, might be 140 meters deep. These boreholes here in this array might be 180 meters deep. So there can be a significant variation in the depths of the boreholes. The hydraulically separate, as I say, but they are thermally in contact. So anybody who's designing these things really does need to know what they're doing. Any questions coming in on that, Stephen?
Sorry, Chris, just a bit of a technical hitch there.
Right.
Right. Is there a rigorous method for estimating diversity of flow rate in these systems?
There isn't a published document on it. We design to our standards that we agree with our heat pump manufacturer customers. And it does vary depending on the manufacturer of the heat pump. So to give you a flavour for what that looks like, particularly with flow rate diversity, it would be over designing a network if you designed for optimum flow rate with 100% of the units running. When you've got 100% of your units running, you would actually design to the minimum flow rate for those heat pumps. So that gives you that leeway to take that diversity in there. So we do it in agreement with the heat pump manufacturers we're working with. Great question.
Cheers, Chris. That's no more at the moment.
Really, really good question. Okay, right. So I've talked about domestic heat networks mainly. Let's talk about more industrial stuff, because this ambient heat network concept applies not just to domestic buildings.
and it doesn't just apply to commercial buildings, it applies also to mixes of domestic and commercial buildings, which is, excuse me, in many ways the most exciting bit of what's going on at the moment. So let's look at a conventional heat network here. We've got a boiler or a CHP unit, whatever it is, delivering high temperature water through a high temperature heat network. And if we've also got a cooling heat network going on, we've perhaps got some heat pumps rejecting heat off to a cooler on the roof, and that will be taking heat back in to the heat network. And if you're doing this right, you know, you really want to be taking some of that heat and recovering it somehow into that heat network as well. So you can start to get quite sophisticated about recovering heat, but that heat recovery can only be done instantaneously. Okay, you can't recover heat over a longer period of time. So that's a conventional heating and cooling network. Perhaps this is a supermarket and these are dwellings, or they could be commercial buildings, or doesn't matter, they are heat uses. And the more we connect together, again, we're taking advantage of the diversity there to improve efficiency. So that's a conventional, maybe a third or fourth generation heat network. Let's now look at an ideal world example of, we could actually put heat pumps in all of those dwellings and all of those commercial buildings now. And if we had a really nice thermal balance all year round, we could just leave it at that. We could just connect these buildings in and move heat around throughout that heat network. But obviously the chances of that remaining in balance all year round is pretty slim. Okay, so in that instance, your ground loop becomes your energy recovery medium. It doesn't only recover energy, but it recovers energy instantaneously, it recovers energy interseasonally, and it gives you the excess, it takes away the excess or gives you the deficit. So it can act in both directions, either pushing heat out into the ground, or it can act sucking heat into the ground, and it can do so dynamically. And it can also do so without being controlled, because these heat networks, ground source heat networks, are designed, not controlled. So these heat pumps can just turn on and off to suit themselves, and they can either reject heat into that heat network, or they can suck heat back out, or they can do it in a mix mode. So provided we know enough about the profile of those loads in the building, then we can design that heat network to be sustainable without any real control over that central infrastructure. So that's the benefit of ground source, particularly when we're talking about mixed loads. So if you're an energy manager at a university estate, for example, you've got a nice big greenfield site in the middle of your estate where you could put some boreholes in, this is a great solution for you, because you're almost certainly going to have a very diverse load profile around that estate. Just as an example, could be a hospital, could be anything else, doesn't really matter. But the more diversity you've got in your buildings, the more attractive a solution this can be. Okay. So why stop there? Why stop there? We can actually start now to connect these heat networks together. Now, this is particularly relevant when we start talking about heat network zoning, which is under consultation and discussion at the moment, potentially allowing local authorities to declare a heat network zone. And this could be a heat network zone declared here in next year, and this other one here could come to plus 2 years later, something like that. We can keep those two heat networks hydraulically separate, but we could put a heat exchanger in between them, which allows heat to flow between those two heat networks. And that's only going to improve the efficiency, because they are going to be diverse. There's going to be diversity of loads between those heat networks. So it's only going to improve efficiency. So that would be the connection of two 5th generation or 2 ambient heat networks. But again, you can go further. You can start to connect up not just those ambient heat networks, but you can start to connect other sources of heat into it. I touched on solar earlier on, but you could also connect, say, a 3rd generation or 4th generation heat network in. A common problem in those previous generation heat networks is higher than ideal return temperatures. So you could potentially dump some of that excess heat into your 5th generation heat network. So lots of flexibility, lots of opportunity to take advantage of these as a cornerstone, if you like, of decarbonising and generating more networked systems, more heat networks. Okay, Stephen, I'll go zoom right out. I might zoom back in again and do some sketching, but I'll take any questions.
None pending at the moment, Chris.
Oh. Well, what Kira's done then. Cool. Okay. Well, if there's no Go on.
Hang on. Someone's
Typing. Like
another comment. It says here another comment. I'll just wait. Here we go. Oh, excellent presentation. There you go, Chris.
Love it. Thank you very much indeed. Love it to get some nice feedback. Thank you very much indeed.
Again, some thank yous there. If I just can interrupt as well, if you go into the event side of the website, you'll see webinars. You'll see this one actually, hopefully this afternoon when it's downloaded, and you can catch up as well on our YouTube channel where they all are effectively. So if anyone wants to delve back into our archives, absolutely tons of info on there, from basic stuff to if you're considering to get in a ground source heat pump to things like you're doing, Chris, and other stuff like that as well. So just wanted to put that out there for everyone who needs some more resources. Free to use at the moment.
It is an excellent resource, it has to be said, and some brilliant speakers on there, real experts in their field, and some really excellent material on there. And just to build on that, we obviously stream 1 will be a more detailed training course with certificates issued at the end and tests and everything else. So do look at that if you are interested in developing your knowledge a little bit further.
I have got a question for you, Chris, as well, actually.
Brilliant.
From Dan. Is there any live data of any ambient loop networks?
Yes, quite a lot of it. Actually, with one of our customers yesterday, I was analysing be about 15 networks across 6 or 7 sites, analysing performance data for that and looking at how the performance of the network is diverging from the predicted performance of the network. And the main reason it diverges is because of the occupancy being slightly different, or the usage of that heat network being slightly different as well. So it's very interesting. We're starting to get some good data through. There's also some good data out there on larger systems that were installed historically. So back about 15 years ago, there was quite a lot of larger scale systems going in, and we've got some performance data coming in on that. There is, if you have a look on our website, there is some performance data for stuff we've designed. I think, Stephen, have we got any real performance data on the Ground Source Heat Pump Association website yet?
Not as I'm aware of, no.
Not aware of.
Quite a lot on there, so there might be something hidden away in a corner somewhere, but not to mind anyway.
Another excellent section on the Ground Source Heat Pump Association website is the members list. So many of those members will have performance data published on the websites. There's other universities as well. London South Bank, for example, have done quite a lot of work, as have University of London on that. So yeah, and I don't mean to, there's Southampton University, Bristol University, Leeds University have all been building up information. So it's worth a trawl on the internet. And if you do want anything specific, do contact myself or Stephen, and we'll see if we can dig something out for you.
Right, Chris, I've just been asked, do you know of any modelling tool for such 5th generation networks with boreholes?
Yeah, there are. So I think I did a webinar on this, but it might have been one of the Stream 1 learning videos. I can't quite remember. We'll have to check for you. But there are a number of commercially available packages for ground loop design, which will include, to some degree, the hydraulics of those systems. The package, the two packages we use at Genius Energy Lab would be GLD by Gaia Geothermal. The other one would be EED, Earth Energy Designer by Blocon. It's a Swedish package. They have got their strengths and weaknesses. Personally, I use GLD more because it's got an accurate heat pump model built into it, and I think that's quite important for the designs to have that heat pump model built into it. What I would say, however, is if you're going to buy one of those packages and start designing it, it's important to build into the business case for that purchase some training. It really is important to build that training in, because they are not packages that you can just pick up by playing around with them. They are quite detailed packages. And the other point I'd make on that is getting trained on the software itself is just part of it. There's an awful lot of knowledge that's required around it. So yeah, whilst you can get trained up on the packages, the manufacturers will offer training. We offer training in our business, for example. I was training a gentleman last week on the use of GLD. So But I would say that don't take that knowledge in isolation, because you've got to understand geology, you've got to understand hydraulics beyond the scope of the design packages. You've got to really understand building physics to get that right. When you start to also talk about heat recovery, that adds another layer of complexity on there. So by all means, get trained up and do it. It might be easier if you're only doing a few of these to get onto the Ground Source Heat Pump Association website and have a look under the consultant section. You'll see Genius Energy Lab in there and other companies in there who will be able to design these systems for you. So yeah, it's up to you whether you take the skills in-house or buy it in.
Right, that's everything, I think, Chris.
Okay. All right. Well, thank you, Stephen, and thank you, everybody, for your attendance today. I found that really interesting. Thanks for the excellent questions. Hopefully you enjoyed the whiteboard format as opposed to just a regular old PowerPoint. We're getting great feedback about it, so that's good. So thank you, Stephen.
Bye, everyone. Thank you.
Bye-bye.